Okay, we're going to take a look today at what we call Euler's method. Here's Leonhard Euler. He's made a whole bunch of contributions to math. Here are some of the things you can thank him for. Okay, so there are many differential equations that cannot be solved. Remember that a differential equation is an equation that contains a derivative, y prime or y double prime. Even if we have a differential equation that we can't find the antiderivative of, we can still approximate solutions. And we've seen one way to deal with this is by using a slope field, and we can get an idea visually of what the graph looks like. Euler's method is sort of an extension of slope fields. If we know a point that our function goes through and we know the differential equation, we can come up with an approximate sketch of what that curve is going to look like. So we want to construct a graph showing what the solution to dy dx equals 2x looks like if the solution goes through 0, 1. Now, with this, we could take the antiderivative, get x squared, and we could solve exactly. We're just using this as an example of the method that we could use. Now, we're going to specify our x intervals as being 0.5. So since this is an approximation method, what we do is we start that 0, 1, and we keep on moving over to the right in the x direction using intervals of 0.5. So we're going to approximate the y value when x is 0.5, and then we can approximate the y value when x is 1, and so on. Okay, so we know our differential equation dy dx equals 2x. We know the solution goes through the 0, 1, and we've established that we're going to use values of delta x for this, of delta x equals 0.5 for this example. Okay, so I have these three columns here. The first column, n, that's just there to keep track of how many iterations of Euler's method we've used. So n equals 0 stands for the initial step. Now, on the initial step, we're given that x equals 0 and y equals 1. So we can plot that point right there in our graph. dy dx, we know that that's 2x. So at the point that we're given, x equals 0, so dy dx is 2 times 0, or 0. And we know that dy dx is the exact change in y over x, which can be used as an approximation for delta y over delta x, because delta y and delta x are some sort of a finite change in y and x. So if we rearrange this, that means dy dx times delta x is approximately equal to delta y. So if we want to find our change in y, we can take dy dx, which is 0, times our change in x, which is always going to be 0.5 for this example. 0 times 0.5 means y changes 0. So our next point we're going to find, since x is changed by 0.5, that means x is going to be 0.5. And our next y value is the original y value plus delta y. So our next y value is 1 because y was 1 and it changed 0. So on the next step, we'll call that step 1. X is 0.5, y is 1, and then dy dx, since that's 2 times x, that's going to be 2 times 0.5, which is 1. Delta y is dy dx times delta x, so that's 1 times 0.5. And y goes from 1, increases by 0.5, so now it's 1.5. So now on the next step, x increases by 0.5, so now it's 1. We bring down that y sub n plus 1, so now our next y value is 1.5. dy dx is going to be 2. Delta y is dy dx times delta x. 2 times 0.5 is 1. And y goes from 1.5 to now 2.5. Okay, so we go from y equals 1.5 to y equals 2.5. We can see that next line segment. And we go through this again, find dy dx, find delta y. Y goes from 2.5, increases by 1.5, so now it's 4. So when x is 2, y is 4. And if we compare this to the exact solution, because we know how to solve dy dx equals 2x, that gives us y equals x squared plus c. Since we know this goes through the 0, 1, we can solve for c, and we get y equals x squared plus 1. And if we graph that along with our approximation here, we can see how those look very similar. Now, clearly the approximation is not exact. It's over a little bit too far to the right. And this could have been corrected, or we could have had a better approximation if we'd used smaller values of delta x. For example, if we use delta x equals 0.1, this approximation would be much closer to the true value. So this is what we refer to as Euler's method. As I was saying, this is more accurate if delta x is smaller, and this approximation gets less accurate the further we move from the initial value.